Once we've created functions that are symmetry-adapted linear combinations of our atomic orbitals, this actually gives us a special new ability that we may not have had before, and that is the ability to predict whether or not certain integrals that we may need to evaluate would be zero or not based on symmetry considerations. The sort of integrals I'm thinking about are things like overlap integrals, so that might be something of the form that looks like this, or Hamiltonian integrals that have the form that looks similarly like this, where we're evaluating matrix elements, we're evaluating integrals over two different functions, psi sub I and psi sub j. And our supposition is going to be if we can say something definitive about the symmetry of these functions, that will allow us to make some predictions about how these integrals turn out. All right, now we have created symmetry-adapted functions where they belong to a particular irreducible representation. I'll call it gamma sub k. Now, I'm going to use the subscript advisedly to tell me which of the irreducible representations a function belongs to. So, for example, if I write psi sub k, I mean that it belongs to the irreducible representation gamma sub k. So these would be, for example, functions that would belong to the irreducible representations I and j, which may or may not be the same irreducible representation. In other words, these could be two functions that belong to the same irreducible representation, or they don't. Now, just to give you an example of what sort of the meaning of this would be, remember that one of the linear combinations we found that belong to the AU representation, that's the AU representation of C2H, so this is reproduced here, and this is for the molecule butadiene. So again, show you that we're labeling the four atoms 1 through 4. So 1 and 4 represent at the two ends of the atoms, and 2 and 3 are the two ones in the middle. All right, so Phi1 plus Phi4 would be the pz orbital on carbon 1 and the pz orbital on carbon 4. And when I add them together, I end up with a symmetry-adapted function that has something to do with the AU symmetry. All right, exactly what does it have to do with that AU symmetry? Well, let's suppose, for example, I took the identity operator and operated it on Phi1 plus Phi4. I think it's easy to see, because the identity operator doesn't change anything, that I would just get Phi1 plus Phi4 back. If I did the same thing for C2, though, what would I get? Well, it would basically switch the positions. These would rotate around, this would rotate around, but I would still get Phi1 plus Phi4. Likewise, if I did this for the inversion operation, what will I get? Well, the inversion operation switches the positions, but it also projects down through the center of the molecule, so it actually flips the sign. So in this case, I'm going to get negative Phi1 plus Phi4. And I'm running out of space here. Sorry about that. Similarly, if I do this for sigma h on Phi1 plus Phi4, it will keep the two orbitals in place, but it will flip them relative to the plane of the molecule. So they'll again end up with minus Phi1 plus Phi4. So I've done all of this basically to demonstrate that the effect of the symmetry operation on this particular function in each case is to generate a multiple by 1, a multiple by 1, a multiple here of negative 1, and a multiple here of negative 1. So I have 1, 1, minus 1, minus 1, and these are precisely the characters that we find for the AU representation in the C2H character table. All right, what does this mean? This means that Phi1 plus Phi4, and I'll write it formally here, Phi1 plus Phi4 is a basis for the AU representation. All right, and so what that means in practical terms is if I ever want to operate some symmetry operation on this function, I will simply get the character that represents that operation times the function. All right, this is true for any time we have a function that can serve as a basis for an irreducible representation is that the operation of the operator simply gives the character times the function. All right, so that is a great labor-saving device, as we shall see. All right, now let's suppose that I'm interested in a particular overlap integral between two functions that may or may not belong to the same irreducible representation. Their representations would be I and j. All right, so I'll represent that as phi sub I, phi sub j, or write it as an integral. And I'm going to space this out a little bit so I can add stuff later. Phi sub I star, phi sub j, d tau. All right, now the thing that I may want to add here is, what if I were to exercise one of these symmetry operations on this whole overlap integral operation? So in other words, I'm going to take a symmetry operation from the C2H group, or whatever point group I happen to be in, and exercise it on this overlap integral. All right, that is in effect the same as making that symmetry operation apply to each of the functions in the integral. All right, now if these functions belong to these irreducible representations, the result of this symmetry operation will be as follows. I'll end up with the integral, and here I'll have chi sub I for that symmetry operation, multiplying by psi I star, and here I'll have chi sub j operating on this times psi sub j and integrating. Okay, but these two things are not they're not part of the integration variables, so these can actually be brought out front of the integral. So this will equal chi sub I r, chi sub j r, multiplying this integral but this integral is just Sij. So I've done all of this, and it may feel like I'm working in circles, but you'll see that there's a point to this in just a moment. All right, what I would like to convince you of is that any symmetry operation on something like an overlap integral will actually not affect the overlap integral. In other words, if I were to simply reflect everything in a plane, that overlap integral will still have the same value. If I were to rotate it about an axis, that will have the same value. Even if I invert it, those two functions will have the same value of overlap. So in fact, this whole thing is still equal to Sij, because this is equal to Sij. All right, so what does that mean? What does this mean? How can we interpret that? Well, since these have to be equal, there's two ways we can make them equal. We can make them equal if this product of things is equal to 1. So our first condition is that chi sub I of r times chi sub j of r equals 1, but it has to equal 1 for all possible symmetry operations in that point group. All right, the only time this is going to be true, that this product is equal to 1 for all of these symmetry operations, is if I equals j. All right, the two irreducible representations are the same. So in other words, both of the functions that are involved in this overlap integral belong to the same irreducible representation. There's another way, however, that we can generate this equality, and that is if this particular overlap integral equals 0. So essentially what this demonstrates is that we will get 0 overlap if psi I and psi j belong to different irreducible representations. All right, that's a powerful result. It tells us automatically now if they don't belong to the same irreducible representation that we can effectively ignore that overlap. It's going to be 0. Now, this also has implications for the Hamiltonian integrals, and it works as follows. The Hamiltonian operator should not depend upon the orientation of a molecule in space, so the Hamiltonian operator itself is invariant to symmetry operations. That is, symmetry operations that work on the system as a whole. So what does that mean? All right, well, if I write my matrix element, or my evaluation of hij is psi I, h, psi j, and that's simply going to be the integral of psi I star h psi j d tau. Now I can do the same thing that I did before and say, what if I were to perform one of those symmetry operations on this whole thing? So I'm going to perform a symmetry operation on this hij, which is equivalent to the symmetry operation operating on the Hamiltonian and on each of the wave functions in this integral. Well, this, I'm going to say, is just the Hamiltonian again, because the Hamiltonian, in effect, belongs to the totally symmetric irreducible representation. So it's just 1 times the Hamiltonian. So I guess what I'm trying to say is this. This will always be true. All right, what about the rest of this? Well, we'll get something out that is similar to what we got before. We'll get chi sub I r, chi sub j r times hij, because the rest of this will return and give us back something like this. Okay, but this must be equal to hij, so again, this is going to be equal to, this part will be equal to either I equals j, so that this is equal to 1, or hij is equal to 0. So once again, if the two wave functions are belonging to different irreducible representations, this integral over the Hamiltonian will end up vanishing unless they're in the same irreducible representation. And that's just a way of taking advantage of the fact that the Hamiltonian itself is a totally symmetric object within this point group and within this set of symmetry operations.